Hi, everybody. We are back, and in this segment, we're going to start jumping into an idea known as statistical hypothesis testing. And what we're essentially going to formalize is how we can conclude whether or not something is what we call statistically significant. Whether or not we see an effect that is very far away from where we expect it to be, such that we can conclude that that effect is actually there. It's not just attributed to some small random noise. And I think the best way to start this is by motivating it with an example in particular here. So let's suppose your business is planning on bringing a new product to market. Maybe you're Elon Musk and you are coming out with a new battery technology for Tesla. And we want to know whether or not the new model is sufficiently outperforming the old model. Or equivalently, this situation here that we're going to look at, where the plan of bringing the new product to market is only going to succeed if the following conditions are met. First and foremost, we need the cost of production to be less than $10 per unit. And we need more than 20% of our target market willing to pay at least $25 to purchase the product, meaning in some regard, we're making at least a reasonable margin here. So we're going to go ahead and think about a hypothesis test related specifically to this first point here. Is our cost of production reasonably low enough for us to go ahead and engage? So we want to figure out whether or not we should proceed with the new product launch or if it is too costly for us to do that. And let's assume here that the cost of production can be modeled as a continuous random variable. And we can conduct a random sample of the manufacturing process and collect cost data as our product comes off the assembly line. And let's suppose here we randomly sampled 40 units off of the production line. And we noted from that sample that the average cost is $9. The question is, what can we conclude? Okay, and the answer here is, well, it's kind of difficult to conclude anything at this point because we know if we had selected 40 different end products off the production runs, the average is going to move around a little bit. There's some sampling noise here. So I guess the question is this $9 a fluke, or are we actually underneath the required $10 threshold to bring this product to market? And in order to answer this question, we're going to have to think about testing an appropriate hypothesis to determine whether or not that $9 sample mean that we saw is sufficiently far enough below the $10 requirement. Okay, so that's the idea, is we want to statistically formalize the thought of how far is too far. How far away would that sample mean need to be, or how far below $10 would it need to be to the point where we could be confident that we've met this $10 cost requirement and we can comfortably bring that product to market. Okay, so we're going to come back to this. We're going to talk a little bit about a few important ideas related to hypothesis testing. And the first one is that a hypothesis itself is an assumption about the population parameter, and it need not be a true assumption, which is why we are testing it. We're going to consider in this course specifically testing the population mean mu, but in your book and your readings, you might also see examples where they test the population proportion. And we should be okay with that. The way you calculate the mean is a little bit different and the standard error is a little bit different, but otherwise everything we're going to discuss here in terms of running a critical value hypothesis test or a p-value hypothesis test on the mean will generally apply to the population proportion as well. So here's an example of a hypothesis. We're hypothesizing here that the mean monthly cell phone bill is at least $92. Okay, that's an example of a hypothesis. If we wanted to find evidence to show that this is accurate, an accurate assumption here, we would be looking for sample means that are very high relative to that $92 threshold. However, the approach we're going to take is we're actually going to look for evidence that disproves this. Okay, and just like in any logical situation, if you were thinking about a true-false question, okay, is it true or is it false? That's essentially the approach we are going to take here. In general, I would argue it is much easier to show that a statement is false than to show that it is true. And if you think about the statement that all swans are white, and consider that statement, all swans are white. Okay, if I wanted to show that that statement was true, what would I have to do to convince you? Well, if I wanted to prove that it was true, I would literally have to catch every swan in the world and show you that they're all white. And that is very, very costly. However, to disprove a statement, the only thing I need to do to disprove it is I need one viable counterexample, meaning I would only need to show you one swan that is not white, and that would do it for me. And that is the approach we're going to take here. So we may have some assumption or some hypothesis about the mean, and we're going to look for statistical evidence in some sense to disprove this hypothesis. Now, this hypothesis that we're kind of starting with here, that's the status quo of our framework, is known as the null hypothesis. And we reference this with a capital H sub 0 or sub naught. And the null hypothesis states the assumption to be tested. Okay, in our example here, the null hypothesis is that the population mean phone bill is greater than $92. And one thing you should be aware of when stating a null hypothesis is that it is always stated in terms of a population parameter, never about a sample statistic here. So you should never see X bar showing up when we're thinking about a hypothesis test related to the population mean. Okay, so the way we're going to start approaching this is we're going to start with the null hypothesis, and we're going to begin with the assumption that the null hypothesis is true. Okay, we're going to assume it's true, and then we're going to start looking for evidence. So this is very similar to how the US justice systems works in some regards, right? You are innocent until proven guilty. Okay, so the status quo here, the null hypothesis, we're going to think about that as you're initially innocent. And we're going to look at the efficacy of this status quo or this maintained hypothesis by trying to find evidence against it. Now, how good is the evidence? Well, that depends on how far away from our hypothesis the evidence actually falls. One hint that you're dealing with a null hypothesis is that the null hypothesis always contains some form of inequality, either an equal signal, a less than or equal sign, or a greater than or equal sign. Okay, and again, just like a true statement, okay, we're not going to be able to really prove a null hypothesis is true. Okay, we'll be able to fail to find enough evidence against it, but we're not going to be able to catch every white swan in this analogy, in this framework here. Okay, now the complementary event, or the opposite of the null hypothesis here, is something known as the alternative hypothesis. And in our example, with respect to this monthly cell phone bill, if the null hypothesis was that it was at least $92, then the complementary event there would be that the alternative hypothesis, H sub A, is that the population mean is strictly less than $92. And we can think about this as the challenge to the status quo, okay, also known as the action alternative. And one way you know you're dealing with a properly specified null hypothesis here is an alternative hypothesis here is that the alternative hypothesis will never contain inequality in any form. No equal sign, no greater than or equal to, no less than or equal to. It'll contain strict inequalities like the strict greater than or less than sign, or the not equals sign in the case of what we call a two-tailed test. But this is the idea. We have some presumption, some null hypothesis about how we think things are, and then we're going to look for statistical evidence against that, really in support of the alternative hypothesis. Now, we're not proving anything true. Okay? We are just looking for evidence to disprove things. We're looking for that black swan, if you will. Okay, so the general logic of the hypothesis test here is that we're essentially going to construct a statistical proof by contradiction. We're going to assume that the null hypothesis is true and look for evidence sufficiently far away from our hypothesized value to suggest that it is false. So again, our null hypothesis, this is the status quo. This is our formalized statement about the population parameter that we are assuming to be valid. Okay, is it valid? May or may not be. We're going to look for evidence against that. Just like, is the defendant innocent? They may or may not be, but we're going to presume they are until we find sufficient evidence against that claim. The alternative hypothesis is our alternate action or our research hypothesis. This is what we want to quote unquote prove here. And this word prove, I want to be careful with that because we're not going to prove the alternative is true. We're just going to show that it is in some sense a better assessment of reality than the null hypothesis. And we hope experimental evidence will suggest the alternative hypothesis, again, is not exactly true, but it is better than the null hypothesis by showing the null hypothesis is unlikely to be true in the face of this counter evidence. So in terms of developing null and alternative hypotheses, okay, again, the alternative hypotheses is a research hypothesis. So if we were, for example, developing some sort of new marketing strategy that is believed to be better than the current strategy, our alternative hypothesis here might be that the new marketing strategy is better, and we're trying to look for evidence in that direction. Okay? Are we converting to a lot more sales than we were under the previous? The null hypothesis would be that the new strategy is no better than the original status quo. Okay? So we would look for data that helps us confirm the alternate hypothesis by invalidating the null hypothesis. So let's look at another example here of how to think about this. Again, as the research hypothesis, maybe a new Salesforce bonus plan is developed in an attempt to incentivize better salesmanship and in order to increase sales. So the alternative hypothesis could be here that the new bonus plan does increase sales. Okay. And we're looking for evidence that says, hey, after the fact, after we implemented this change, the sales values are very, very high relative to what they were originally. The null hypothesis would be consistent with the status quo, which is that the new plan does not have a statistically significant effect. And it doesn't change the status quo. So again, we're looking for information essentially to invalidate the null hypothesis in an effort to really to confirm the alternative hypothesis in favor. So we're not really proving anything true. We are trying to show significant evidence against the null hypothesis claim. All right, let's go ahead and take a look at some more examples. Let's suppose that we're considering the problem of testing the mean weight of cereal in a cereal box, whether or not it differs from 18 ounces. Believe it or not, there are laws called slack fill laws, which place legal restrictions on how much of a box of product can be filled with empty space because they do not want manufacturers misleading consumers. So we're going to test some cereal boxes here. We want to see if the mean weight of cereal in a box differs from 18 ounces. So the first step here is to state the question statistically. And I'm actually going to start in this case with the alternative hypothesis here, in that we want to show that the mean is different than 18. We didn't say higher or lower, we just said different. And you can tell this is an alternative hypothesis because of the not equal sign. Remember, the alternative hypothesis never contains an equal sign in any form. Okay, the opposite, the complement of that event, would be that the mean is equal to 18. Okay, again, note the alternative and the null. Okay, the alternative being the top one, the null being the bottom one. They are mutually exclusive and collectively exhaustive events. Now, which one is the null? Well, we already saw that because this equality shows up here, the null has to be that mu is equal to 18. Okay, that is what we are trying to show. And it has the right sign here. So let's go ahead and take a look at this next example where we want to identify a properly specified null and alternative hypothesis. Okay, choice A says the mean number of years Americans work before retiring is 34. B says the mean starting salary for USD graduates is at least $55,000 per year. C says 75 out of every 100 people who go to the movies on Saturday night buy popcorn. That's related to the population proportion P. And the average household has 3 tablets is choice D. Now, hopefully, if you remember what we had talked about in terms of specifying hypotheses, they're never specified about sample parameters. Okay, so you might want to pause it, think to yourself, which choices can I get rid of right away because they refer to sample parameters? And those are choices C and D. C refers to the sample parameter P bar, which is the sample population proportion. D refers to the sample parameter X bar, which is the sample mean. Okay, so C and D are out right away. And if you look at the difference between A and B, you'll notice B has an interesting faux pas in that the null hypothesis doesn't contain an equal sign. It's got a strict inequality here. And the alternative hypothesis has a greater than or equal sign, which it should never have, right? The alternative hypothesis should never have an equal sign. So that being said, the best answer here is A, which has correctly stipulated the null and alternative hypotheses associated with that hypothesis test. Okay, so in terms of our logic for hypothesis testing, we're going to do the following. If the null hypothesis is rejected, we're going to think about us having in some sense proven or provided more evidence in favor of the alternative hypothesis. And again, we're not proving anything true. So this word proven here should be taken somewhat with a grain of salt. And if the null hypothesis is not rejected, okay, then we basically were unable to find any swans that were not white, but that doesn't mean they don't exist. And we just weren't able to find enough evidence to be able to prove that innocent person guilty. Couldn't do it. Okay, were they guilty? Maybe they were, but we didn't have enough evidence, so we could not reject that status quo. So the way we would make concluding statements, and there's a correct way, there are some incorrect ways, but the correct way to say things is there is not enough evidence to reject the null hypothesis. And the incorrect way to say this is that the null hypothesis is correct or the null hypothesis is accepted. We're not accepting it, we just cannot reject it. Okay? And it's important to continuously retest hypotheses as new data becomes available because the structure of uncertainty could be changing over time. So take a moment, look at this next question and see if you can hone in on the correct answer. And if you need to pause the video, go ahead. Okay, so which of the following statements is correct? The best answer here is choice B. Since the sample evidence cannot be supported by the null hypothesis, I reject the null hypothesis. Okay. Note D, I can reject a given claim if the null hypothesis is not rejected. That is incorrect. C, I can establish a given claim if the sample evidence is consistent with the null hypothesis. We're not proving anything true. We're not finding every white swan. So that's not what's happening in C. That's not correct. And A, I accept the null hypothesis since the sample evidence is not consistent with the null hypothesis. That's the opposite of what you would want to do. If you have evidence that's not consistent with your hypothesis, you definitely don't want to be accepting it. Okay, so let's go ahead and summarize the hypothesis testing process here diagrammatically. Okay, let's suppose the claim is that the population mean age of a video gamer is 15 years old. So this is our claim about the population parameter. It's our status quo. What are we going to do? Well, we're going to go to the population and we are going to randomly sample some individuals. So those guys that are kind of grayed out there in some darker blue, we select those 4 from our sample. And then we use that sample to calculate our best guess about mu. Okay, so let's suppose here that in our sample, it turns out the average age of the gamer is 35. Okay, now the question becomes, is 35 far enough away from 15 for us to say that our claim that the average age was 15 is not reasonable. Okay, is it likely we would observe a sample mean of 35 if the null hypothesis was true? And if the answer is no, not likely, then we would want to reject that null hypothesis. So again, we're back to this idea that we're looking for evidence that is sufficiently far away from our claim. And if the evidence is far enough away from our claim, then we can conclude that the claim is not reasonable. So diagrammatically here, we're thinking about the sampling distribution of X bar. And if the mean was at 15 here under the null hypothesis, it's pretty unlikely that we would observe a value as extreme as 35. And if we were to use our z-score approach, we could convert 35 into a z-value, and we could actually calculate the probability in this upper tail, which would be the probability of observing something more extreme than 35. And if that probability is extremely low, if that probability of observing something more extreme than 35 is very low, then that must mean that the fact we observed 35 to begin with must already be very extreme if the likelihood of observing something more extreme is close to 0. So we're going to pick up with this idea in the next segment, discussing what are known as type 1 and type 2 errors related to false positives and false negatives. Hope you enjoyed this intro, and I will see you soon.